Yeah, good morning. In this session, I would like to demonstrate certain aspects of equation-oriented simulation. In fact, to solve this kind of a problem using design spec. Is you should be able to run the problem at least once in sequential modular approach. Let me show you as an alternate to using design spec. So as you can see from the problem statement, it's a very simple problem. It's a mixer. Toluene and ethylene are getting mixed. So the rate of toluene, temperature and pressure, and we know the temperature and pressure of the other stream, ethylene stream. So we wanted to obtain, after mixing, a temperature of 85 degrees Fahrenheit at the exit. Now we need to calculate the flow rate of ethylene that would give us the required temperature at the exit. Problem. So we are using two components in this, toluene and ethylene. So let us define those two components first. Okay. Go to next input screen. So you can choose a property model. Go to next, choose simulation environment, create your problem. So we are using a mixer, connect input streams. Let me rename them. So toluene, let me choose the system as engineering. So this is ethylene stream, which is entering at 50 degrees Fahrenheit and a pressure of 1 bar. And we don't know the flow rate of this ethylene stream. Let me make some guess. Say, I think the flow rate of toluene is given in lb per hour. So let us also make some guess with respect to the mass flow. Let's say about 100 or maybe equivalent to 1000. Doesn't matter. Anyway, it's a wild guess. So we have defined the ethylene stream. Next. So the toluene stream is entering at 100 degrees Fahrenheit, 1 bar and 1000 lb per hour. And the mass flow is 1000 lb per hour. So next. We're able to run the simulation, stream summary. Now you can see, so ethylene stream is entering at 50 and toluene stream is entering at 100. The outlet temperature was 88 because on the assumed flow rate for ethylene, which we have done it as 100 lb per hour, right? Now we can use a design spec to calculate the flow rate of ethylene in order to get the required temperature of 88 at the exit. Let us first solve the problem using a design spec. So as you know, you can use a design spec, new, okay. So our target defined variable, measured variable is outlet temperature, which is a stream variable. Stream, it is also again stream variable. Stream is a product in degrees Fahrenheit. Next. So outlet temperature need to be at 85. What is that we are trying to vary? So we have assumed a flow rate of ethylene stream. So let us take this as stream variable. Stream is ethylene, variable is mass flow. We started with 100, so let me consider 100 to maybe 1000. So this is the guess. Now you can see the design spec is going to operate. So we are starting with an ethylene flow rate of 100 lb per hour. Calculate the mixer, find out the temperature of the product stream, compare with your requirement of 85, otherwise go and adjust the flow rate. So this is how your design spec is going to work. So again, as you know, the default method used is secant and 5 iterations in order to complete a convergent solution. You can see the results. So of ethylene is about 135, we'll be able to get to our required temperature. So we know whenever we have some requirement with respect to the output stream, it becomes a rating problem and analysis problem, and rating problem, if you are trying to solve an analysis problem, requires an iterative solution. So let me also show you another alternate. Let me delete this block, design spec. Okay. Then let me reinitialize and run. Remember, now the solution is based on our initial assumption of the flow rate of ethylene stream being 100. You can see the results. So remember, whenever you want to use equation-oriented approach, you need to run the problem in sequential modular approach at least once. This is needed because only when you run the problem in sequential modular approach, all the variables involved in the problem will be associated with some value. Whether the values are as per your requirement or not doesn't matter. In your simulation will be associated with some set of values. Now, once you run this problem in sequential modular approach, now you can go to the main menu, you can see equation oriented, click on this. By default, Aspen will be using sequential modular approach to solve the problem. Now, I will be able to switch over to equation oriented provided I was able to sequential modular approach at least once. Now I am taking equation oriented approach, then say next. Remember, so EO configuration without this will not be updated or highlighted. Now having chosen this, now this will be available, but anyway let me run it once. So solve equation oriented models. Okay. So you can once again see your results. It will be similar to whatever you have seen earlier. There is no change because we did not do anything. Once you are able to go into equation oriented, expand this EO configuration, then variables involved in your problem. These are all the variables involved in this simulation. Remember, each of these variables, what is the corresponding value, what are the units, what type of variable is it, whether it is calculated or constant, so on and so forth. Right? Now, generally, what I would like to advise you is whenever you want to use equation oriented, you better create a spec group. Right? Say you can name a spec group. So by default it gives some name. Right? Next. Okay, variable. Now this is where you need to be slightly careful in choosing appropriate variables. Let me look at this. Now when you look at these variables, depending on your requirement, you can adjust them according to your convenience. Clicking on specification, so all the calculated variables will be appearing. And once again double clicking, the constant values will be appearing. Now what I mean by constant is the values that we have provided as input. Calculated values represent the value. Now what is our requirement? We wanted to, of course, try to observe how the naming is done, or probably you can see, double click on the value, it arranges from lower value to higher value. Once again double click, it arranges from higher value to lower value. Just now, by running our simulation, we were able to observe the product temperature as 88. Remember, all these are calculated. But be careful in selecting appropriate variable. This is liquid temperature. What I want is combined temperature, in case if it is existing as a liquid or vapor. So I am selecting this variable. Select. So this variable will come. Remember, originally this value as constant. What I mean by constant is I would like to provide a value. So I am looking at a value of 85 degrees Fahrenheit. The variable type is temperature. Degrees Fahrenheit. Any problem? What you have done, a variable which is calculated has been converted into constant. So you need to change another variable from constant to calculated. What we have done earlier, we have assumed the flow rate of ethylene as 100. Now we wanted to calculate the flow rate of ethylene at 100. So there are several variables, but you can see the mass flow, constant. So this is the value ethylene block, ethylene mass flow. Though there are several variables, try to see what is the one that is of to you. This is the variable I have given earlier as an input. So I am going to select this variable. Remember, this was provided as input in the earlier sequential modular. Now I would like the simulator to calculate. So what type of variable is this? This is value is not required because the simulator is going to calculate. This is going to represent the value of mass flow. And the units are lb per hour. So with this spec group, what is that we were able to achieve? We have made a provision to change one variable from calculated to constant, and in other words, we have changed another variable from constant to calculated so that the degrees of freedom remains the same. Now, with this provision, I was able to enter value with respect to a product stream which is not available. This kind of an option is not available in sequential modular approach. Especially when you are using a rating model, you cannot specify any variable associated with the output streams. Now, having done this, let me run the problem. You can see it took a very less time, about 0.01 seconds to reach an answer. So, did we get to our requirement of 85 degrees Fahrenheit with respect to the product stream? This is what we wanted. And you know what is the flow rate, mass flow. So you can see the mass flow is 135.337 as has been calculated by, 135.337 as was calculated even by the design spec. So this way, once you are able to create this kind of a spec group, I can go to spec group and simply add any value that I require with respect to the product temperature. Now from 85, suppose if I want to get a temperature of 80, I'll be able to run the problem again. Of the spec group, look at the results. Now you got to the requirement of 80, and you can see what is the value of this. So the ethylene flow rate 203.183 lb per hour of ethylene flow rate will be able to give me the required temperature of 80. In this way, now by creating a spec group for a given problem, we will be in a position to specify values with respect to an output stream. But remember, you will be able to switch over to equation-oriented approach only when you are able to solve the problem at least once in sequential modular approach. Probably if you go into the details of how equation-oriented simulation is going to work, you will be able to know the limitation why you need to run the problem at least once in sequential modular approach. So, of course, for solving such simple problems, you may not need to go into equation-oriented approach. But especially when you are dealing with complicated flow sheets involving a number of design specs within recycle loops, reaching convergent solution with respect to sequential modular approach sometimes can pose problems. In such a case, reverting to equation oriented approach, you can see this will be quite effective and you will be able to reach the solution quite quickly. So this is the advantage of converting from sequential model approach to equation oriented approach. So with these remarks, I would like to close the current session.